Last class, we discussed the cell potential. In order to determine cell potential, we need electrode potentials. That means cathode potential and anode potential. And you know, potential is the tendency of an electrode to accept electrons, reduction potential. The tendency, it is not possible to measure the tendency. You know it is not possible to measure the tendency. We have tendencies, but can you measure it? No. It is not possible to measure the tendency. So exact value of electrode potential cannot be measured. But we can compare the electrode potentials, which has more electrode potential, which has less electrode potential. And for the comparison, we need a reference electrode. And here you can see an electrode known as standard hydrogen electrode, which can be selected as a reference electrode. It is difficult to maintain, but we can use it as a reference electrode. Here you can see a platinum wire that is fused in a glass tube, and at the end there is a platinum foil which is coated with the finely divided platinum, and this entire setup is inside a glass tube through which we can pass hydrogen gas, and in this electrode it is passed at 1 bar pressure, and this total setup is immersed in 1 molar solution of hydrogen ions. It is hydrogen electrode, and this hydrogen electrode can be taken as the reference electrode, and its potential is arbitrarily fixed as 0. So electrode, if the electrode potential of standard hydroelectrode is 0, then what is the potential of zinc electrode, copper electrode, nickel electrode, magnesium electrode? In that way we can find out comparison with respect to standard hydroelectrode. So it is standard hydroelectrode. It can act as anode or as cathode, that is depending on the other cell to which it is connected. So the important points in standard hydroelectrode: hydrogen is bubbled through platinum wire and it will act as the electrode, and it is immersed in 1 molar hydrogen ions, and the hydrogen pressure of hydrogen is 1 atmosphere. Determination of standard hydroelectrode, determination of electrode potential. The standard hydrogen electrode can be used for the determination of electrode potential. You know, it is not possible to construct a single electrode. Not possible to construct a single electrode. Zinc electrode alone, not possible. Why? Zinc donates electrons, and there should be something to accept that electron. Oxidation and reduction takes place simultaneously. Oxidation alone, impossible. Reduction alone, impossible. So a single electrode also impossible. In a cell, there will be anode and there will be cathode. So if you want to measure electrode potential, you have to construct a cell. In that cell, one of the electrode will be hydrogen electrode. Then we can determine the electrode potential of the other electrode. We know the electrode potential of hydroelectrode is 0. For example, suppose we have to measure the electrode potential of zinc. Construct a cell using zinc and hydrogen. You take zinc as the anode and hydrogen as the anode, and you connect it through a salt bridge and measure the potential difference. You will get the value of 0.76 if the conditions are standard. 0.76. Cell potential, E cell is equal to 0.76. That is equal to E cathode minus E anode. Here hydrogen is taken as the cathode. So 0, you can write here 0. 0 minus E anode. That means electrode potential of zinc. So 0.76 equal to minus E anode or E anode, that is electrode potential of zinc, is equal to minus 0.76. In this way, we can measure electrode potentials of all the non-electrodes. And we can arrange them in the order of their electrode potential, either increasing order or a decreasing order. We can arrange them in the order of the electrode potential, and that arrangement is known as electrochemical series. Electrochemical series. Here all the possible electrodes are arranged, and in this particular arrangement it is in the decreasing order of electrode potential. Electrodes with the positive electrode potentials are arranged first, and it is decreasing as we move down, and here the negative electrode potentials, and ends with the lithium minus 3.05 volt. It is electrochemical series. Electrochemical series. And this electrochemical series is very useful. And what are the important uses of electrochemical series? First, you want to calculate standard cell potential, because in electrochemical series, the cathode potential, standard electrode potential of the cathode and standard electrode potential of the anode are known. So we can find out standard cell potential using the equation E cell is equal to E cathode minus E anode. Electrochemical series, if you refer electrochemical series, there you can see the standard electrode potential. Substitute the values and find out E cell. And second application, to predict which metal can displace another metal from its salt to solution. Already we discussed the electron transfer mechanism. Sorry, electron transfer, competitive electron transfer reactions. Competitive electron transfer reaction. In competitive electron transfer reaction, we mentioned zinc can displace copper. Why zinc is displacing copper? Zinc is more active. The metal with the more negative electrode potential is more active. And here zinc has a negative electrode potential, but copper has a positive electrode potential. So zinc is more active than copper, and zinc can displace copper from its salt solution. So we can generalize metal with a higher negative electrode potential can displace another metal with lower negative electrode potential. Suppose you have a question. Magnesium, two metals, magnesium and silver. Is it possible to store silver nitrate solution in a magnesium vessel? If it is the question, you have to refer the electrode potentials of magnesium and silver in the electrochemical series. And you can see for magnesium a positive electrode potential and silver a negative electrode potential. So surely magnesium can displace silver from its salt solution. So it is impossible to keep silver nitrate solution in magnesium vessel. Next, predict feasibility of a cell reaction. Feasibility means whether the reaction is possible, whether it can produce electricity. Only if the cell potential is positive, that reaction is feasible. That reaction is possible. If cell potential is positive, that reaction is feasible. Then to predict which metal can liberate hydrogen from dilute acids. All the metals with negative electrode potential can liberate hydrogen from dilute acids, because all of them are more active than hydrogen, so they can displace hydrogen from its salt solution, its solution. That means dilute acids. Dilute acids contain H+ ions. So all the metals with negative electrode potential can displace hydrogen from its salt solution. Now, balancing of redox reaction, it is very important. There are two methods. The first one is oxidation number method. You can see the question. Write the net ionic equation for the reaction of potassium dichromate K2Cr2O7 with sodium sulfide Na2SO3 in an acid solution to give chromium 3 ion and the sulfate ion. Okay, the equation is not given, but from the given data, it is possible to write the equation. What is the equation? Potassium dichromate, K2Cr2O7. And we need only the ionic equation. So we can write Cr2O7 2 negative plus Na2SO3. Here also we require only the ion SO3 2 minus. So Cr2O7 2 minus plus SO3 2 minus gives chromium 3 ion Cr3 plus sulfate ion SO4 2 negative. Cr2O7 2 minus plus SO3 2 negative gives Cr3 plus SO4 2 minus. Now assign oxidation number to each of these atoms. First chromium, oxygen has -2 oxidation state. 7 into -2 minus 14. 2 negative charges remaining here. That means 12 negative charges are neutralized by chromium. There are 2 chromium atoms. So the oxidation state of 1 chromium 12 by 2 equal to 6 plus 6. So here we can write plus 6. SO3 2 negative. 3 into -2. Oxygen has -2 oxidation number. 3 into -2 minus 6. 2 negative charges remaining here. That means -4 neutralized by sulfur. Therefore, the oxidation state of sulfur plus 4 here. Cr3 plus. It is an ion with only one atom. Therefore, the oxidation state is its charge. That is 3 plus. Plus SO4 2 minus. Here 4 oxygen atom 4 into -2 minus 8. 2 negative charges remaining here. So -6. -6 is neutralized by sulfur. So sulfur has +6 oxidation state. You have to write it here. Okay, chromium +6, sulfur +4, chromium +3, sulfur +6. So here, in the next step, we have to identify the decrease in oxidation number and increase in oxidation number and make them equal. So here you can see +6 is changing to +3. Oxidation number decreased by 3. When one chromium in the +6 oxidation changes to chromium in +3 state, oxidation number is decreased by 3. But here you can see 2 chromium in the +6 oxidation state changing to 2 chromium in the +3 oxidation state. So what is the total decrease in oxidation number? 6. 6 is the total decrease in oxidation number. Oxidation number decreased by 6 when 2 chromium at a +6 oxidation state changes to 2 chromium +3 oxidation state. In the previous equation, you can see there is only one chromium, and it is to balance these 2 chromium atoms. We are adding 2 here, 2 Cr3 plus. And the next part, you check sulfur reduce its oxidation number increased from +4 to +6, increased by 2, but here decreased by 6. Balance all at here oxidation number and make them equal. You have to find out decrease in oxidation number and increase in oxidation number and make them equal. Here oxidation number sulfur, when sulfur changes to SO3 2 minus changes to SO4 2 negative, the increase in oxidation number 4 to 6, that is 2. Only 2 is the increase in oxidation number, but we have to make it equal to decrease in oxidation number. So when you multiply 2 with 3, you will get 6. So you have to multiply this group with 3. If there are 3 SO3 2 minus, there will be 3 SO4 2 minus. So you have to add 3 here, also here 3. Now 3 into 2, 6. Oxidation state also increased by 6. Now increase and decrease are equal. Now the next step, one more is balance all atoms except the hydrogen and oxygen. You check 2 chromium, 2 chromium, 3s, 3s. Now only oxygen is remaining in the unbalanced state. Next, balancing of oxygen atoms by adding H2 to the deficient side. You have to count oxygen atoms in the reactant side and also in the product side and find out where there is deficiency of oxygen. This side you listen, 7 oxygen atoms plus 3 into 3, 9. 9 oxygen, 7 plus 9, 16. And here 3 into 4, 12 oxygen atoms. So here deficiency of 4 oxygen atoms. So add 4 oxygen atoms here by adding H2O. H2O. When you add H2O, get 4 oxygen atoms here. Now step 5. Finally, balance hydrogen atoms by adding H plus to the deficient side. Why H plus? Because the medium is acidic. The medium is acidic, we can add H plus. So you can identify here 8 hydrogen atoms are present. When we add 4H2O here, 8 hydrogen atoms are present. So in order to equalize the number of hydrogen atoms on either side of the equation, we have to add 8 H plus here. Now this equation is completely balanced. The balanced equation we can check by comparing the charge on either side. If the charges on either side are equal, the equation is balanced. Here 8 positive charge plus 2 negative means 6 positive charge. 3 into 2 negative, 6 minus charge. So 6 plus and 6 minus, total 0. 2 into 3, 6 positive. 3 into 2, 6 negative. Here also 6 plus, 6 minus, total 0. The two sides, the charges are equal, 0 equal to 0. Equation is balanced. Now we can go to another question. Permanganate ion, MnO4 minus, reacts with the bromide ion, Br minus, in basic medium to give manganese dioxide, MnO2, and bromide ion, BrO3 minus. Write the balanced ion equation for the reaction. So first you write skeletal equation, MnO4 minus plus, Br minus gives MnO2 plus, BrO3 minus. And here you listen, the medium is basic medium. Okay, it is the first step. And what is the second step? Assign oxidation number. Manganese 4 into 2, 8, minus 8. 1 is remaining here. So plus 7 is the oxidation state of manganese. Br minus minus 1, the charge. MnO2, 2 into minus 2, minus 4. So manganese plus 4. Bromine, 3 into 2, 6, minus 1 charge is remaining here. So 5. We are in the plus 5 oxidation state. Assign the oxidation numbers here. Manganese plus 7, bromine minus 1, manganese plus 4, bromine plus 5. And here when manganese changes to MnO2, what is the decrease in oxidation number? 3 is the decrease in oxidation number. But when bromide ion, Br in minus 1 oxidation changes to plus 5, Br in plus 5 oxidation state. What is the change in oxidation number? 6 is the change in oxidation number or increase in oxidation. Here only 3, here 6. So we have to multiply MnO4 with 2. If you are multiplying MnO4 with 2, you have to multiply MnO2 also with 2. Thus we can equalize the increase and decrease in the two sides. 2 MnO4 minus gives 2 MnO2. Now what is the decrease? Decrease by 6. Br minus gives BrO3 minus. Now what is the increase? Increase by 6. Both increase and decrease are equal. Now what is the next step? After making them equal, you have to confirm that all the atoms are balanced except hydrogen and oxygen. You check it. 2 manganese, 2 manganese, Br minus, Br minus. That is balanced. Now what is here? 2 into 2, 4 oxygen plus 3, 7. 7 oxygen atoms here, and 2 into 4, 8. 8 oxygen atoms here. There is here a deficiency of 1 oxygen atom. So you have to add H2O here. Oxygen atoms by adding H2O. 1 H2O is added here. Now finally balancing your hydrogen, can you add H plus in the deficient side? No, because the medium is basic. You can add OH minus, but by adding OH minus you cannot balance hydrogen. What is the reason? There is oxygen, then the oxygen atoms may not be balanced. So in order to keep all the atoms balanced, finally the hydrogen atoms are balanced by adding H2O, the required number. How many hydrogen atoms needed? For example, if 3 hydrogen atoms needed, add 3 H2O. If 1 hydrogen atom needed, add 1 H2O to the deficient side. Simultaneously add same number of OH minus to the other side. For example, here 2 hydrogen atoms are present. So in order to equalize it, the opposite side you have to add 2 H2O. Simultaneously you have to add 2 OH minus here. That is described. Okay, what you have to add? 2 H2O here. Simultaneously you have to add 2 OH minus here. Now it is balanced, isn't it? 4 hydrogen here, 2 plus 2, 4 hydrogen here, 2 oxygen plus 2 into 4, 8. 8 plus 2, 10. Here 2 into 2, 4, plus 3, 7, plus 1, 8, plus 2, 10. Oxygen also balanced. Charge, you can check the charge. 2 minus, 1 more minus, total 3 negative. Minus 2 minus 3 negative. Here 3 negative, here also 3 negative. So this equation is balanced. And here finally, here 2 H2O, here 1 H2O. We can cancel this H2O. Then here will remain only 1 H2O and there is no H2O in the product side. You can cancel it. There are 2 H2O and H2O and H2O can be cancelled. Then finally, you can write 2MnO4 minus plus Br minus plus H2O gives 2MnO2 plus BrO3 minus plus 2OH minus 2OH minus. Now the second method, half reaction method. In half reaction method, we will split the redox reaction into oxidation and reduction. Then we will balance them separately, following all the rules that we discussed here. Okay, read the question. Balance the equation showing oxidation of Fe2 plus to Fe3 plus ions by dichromate ions Cr2O7 2 minus in acidic medium, wherein Cr2O7 2 minus ions are reduced to Cr3 plus ions. It is to write the equation. Fe2 plus Cr2O7 2 minus gives Fe3 plus Cr3 plus. That is the equation. Fe2 plus Cr2O7 2 minus gives Fe3 plus Cr3 plus. And you assign the oxidation state, chromium. If you assign oxidation state for chromium, already we discussed +6 is the oxidation state. Here you can see 2 plus increased to 3 plus. So Fe2 plus oxidized to Fe3 plus. Fe2 plus oxidized to Fe3 plus. Cr in +6 oxidation state reduced to Cr3 plus. And for the conversion of Fe2 plus to Fe3 plus, it has to release 1 electron. For the conversion of Cr2, that means 2 Cr in +6 oxidation state to Cr in the +3 oxidation state, here it should get 6 electrons, isn't it? So we can split it into 2 halves. Oxidation half Fe2 plus gives Fe3 plus. Reduction half Cr2O7 2 minus gives Cr3 plus. Split it. And first you balance the oxidation half. Here this equation, Fe2 plus gives Fe3 plus. Here it is balanced, and you write the electrons involved only in this reaction. And already we mentioned when Fe2 plus changes to Fe3 plus, it releases one electron. That one electron, you write that one electron here. This equation is balanced. Now take the reduction reaction and balance it. Here Cr2O7 2 minus changes to Cr3 plus by accepting 6 electrons. Isn't it? Okay, Cr2, therefore we have to write 2 Cr3 plus. For the conversion of chromium, 2 chromium in plus 6 oxidation state to 2 chromium in plus 3 oxidation state, 6 electrons needed. Now, as we already mentioned, chromium atoms are balanced. Now we have to balance oxygen atoms by adding H2O in the deficient side, and finally balance hydrogen by adding H plus in the deficient side, because the medium is acidic. Here 7 oxygen atoms, so add 7 H2O in the deficient side. It is the deficient side. 7 H2O, you can add 7 H2O here in order to balance the 7 oxygen atoms. 7 H2O is added. Here you cannot see any hydrogen. Here 7 into 2, 14 hydrogen atoms are present. Therefore you have to add 14 H plus here. Now this equation is balanced. 2 chromium, 14 H plus, 14 H, 7 to 2, 14. 7 oxygen, disbalanced. Now in order to get the complete balanced equation, we have to add the oxidation half and reduction half. But when you add oxidation half and reduction half, you have to notice here 6 electrons are involved. Here only 1 electron involved. The released electrons only can be absorbed here. So it has to produce 6 electrons. So you have to multiply this equation with the 6. Okay, add equation 1 and 2 after equalizing the number of electrons involved. So 6 into Fe2 plus gives Fe3 plus electron, plus Cr2O7 2 minus plus 6 electron is 14H plus 2 Cr3 plus 7H2O. When you add this 6 electron and 6 electron will cancel each other. And what is remaining? 6 Fe2 plus Cr2O7 2 minus plus 14H plus gives 6 Fe3 plus 2 Cr3 plus 7H2O. So this equation is balanced. So in this way, you can practice the balancing of redox reactions. 2 methods, oxidation number method and half reaction method. There are many problems in your NCERT textbook. In the exercise, take it and try to solve it. If you have any doubt, you can call me. Okay, we can stop it here.